And you will see that what would have been an absolute disaster here will actually make perfect sense here. But let me show you a situation where we will have two functions that are inverses of each other, and where an application of a formula like this would be completely straightforward, and you won't even know where the confusion might come from. And that will be the case because we will anchor our discussion in geometry. And here's how it's going to go. So suppose now we have a curve, and I'll just try to draw a random looking curve. That's actually came out quite elegant. Okay? And suppose that, well, we want to do analysis on it, so we're going to parameterize it. And we'll parameterize it with an arbitrary parameter gamma. And then we want to say, well, gee, that's just one parameter. What's better than a parameter is two parameters. Maybe we want to consider an alternative parameterization. And considering alternative parameterizations is very important in our study. And that's because when we work with the parameterization, we'll want to make sure that we're operating with things in such a way that the answer does not depend on which parameterization we chose. And so we'll ask ourselves, what would happen if we did the same thing but with a different parameterization? And if we get the same answer, then great. Maybe great. Yeah, probably great. But if we don't get the same answer, then what we're doing is meaningless. Because what we're doing is then studying the parameterization and not the curve itself. We want to study the curve, and we want to study its geometric properties. We don't want to study the properties influenced by the arbitrary parameterization, right? So we will always ask that question. Let's introduce another parameter and do the same thing and see if we get the same answer. And we want the answer to be the same. And then we'll say that our analysis is invariant. And invariant means doesn't depend on the parameterization. So suppose there is an alternative parameter, gamma, capital gamma. So we'll have lowercase gamma and capital gamma. And they will be related. To each value of gamma, there corresponds a value of capital gamma. And to each value of capital gamma, there corresponds a value of gamma. A good example would be to say that gamma is, why not, e to the gamma. That's a good way to reparameterize the curve, right? Because it's simple. In fact, we'll think of capital gamma in this context as a function, right? That's what I was just saying. To each little gamma, there corresponds a value of capital gamma. So we can think of capital gamma as a function of little gamma. But it also works in reverse. We can think of lowercase gamma as a function of capital gamma. And in this particular example, it'll be log natural of capital gamma. But even if you abstract yourself from this particular example, you know that these two functions are the inverses of each other. And you have to use a lot of words, because if you recall from 5 minutes ago, we had two different functions, but we used the same letter for their variables. Here, it's two different functions, and we're using different letters for their variables. And it's not that one way is better than the other. You just have to be quick on your feet and look at expressions and know what we're talking about. Okay? So, in this particular example, if lowercase gamma, and so maybe the lowercase gamma has the value of 0 here, and the value of 1 here, and the value of 2 right here. Doesn't have to be equally spaced. And the value of -1 over here. That's a reasonable parameterization, I think. Then capital gamma would have the value of 1 here, the value of e here, right? The value of e squared here, and the value of 1 over e here, right? So two different parameterizations. Okay. Well, when we have two functions, we want to consider their derivatives. How will they be related? Well, we'll know exactly how they will be related, right? Because we just did that, but let's do it again. What does it mean that the two of them are the inverses of each other? We're going to start with this function, lowercase gamma of gamma. And now into this function, I will plug in how capital gamma depends on little gamma. So you go from gamma, which perhaps 0, to the value of capital gamma, which may be 1. And then from that, you plug it into the rule that takes you back. And so, of course, you get gamma. So here's what's a little bit confusing, but you have to get used to that. That the same letter gamma means two different things in this one expression. This gamma acts as a variable, right? So this gamma is this. Where does little gamma equal 0? Right here. Where does little gamma equal 1? Right here. Where does little gamma equal 2? Right here. That's what this gamma means. And it's exactly what this gamma means. What this gamma is this function, right? So it represents a different, the same letter represents a different thing, right? The alternative would be to use a completely different letter for this function. Call it G, right? This would be G of gamma or something like that. But then you end up with just too many letters, and the benefit is negative. It's better to reuse the letter and have to remind yourself what it is that this symbol means than to use a different letter. And because it just becomes a mess, and you'll end up with 26 letters of the English alphabet, and you won't be able to remember what the letter means. So reusing the letter is something that's very commonly done in this field, and we'll do it, and you'll have to get used to it, and we'll do it more than once today. Okay? And so now when I apply the same logic and take the derivatives of both sides, I get, okay, look what I'm going to do. I'm going to drop all functional arguments. What I'm about to write will have no parentheses. And you will see that what would have been an absolute disaster here will actually make perfect sense here. So here's my conclusion, that the derivative of gamma, where this capital gamma is this, it's the function, is 1 over little gamma prime, where gamma prime is this function. Okay, so whenever you look at a symbol, lowercase gamma or capital gamma, in any context, you have to tell yourself, is it gamma the parameter or gamma the function that relates the two parameters? So, parameter, function, function, parameter. Function, function, parameter, function, parameter. 1. Function, function. Right? So, I want to double down on the point that I just made. If I erase the functional arguments here, look, it's now a very simple relationship, but it's completely wrong. The derivative of f and the derivative of g are not the reciprocals of each other. Where these functions are evaluated is of not just paramount importance. That's what the relationship is about, right? It's a critical part of the relationship is where this derivative is evaluated. If you don't specify it, it's just plain wrong, okay? But here, it's clear that because we're talking about a curve, and I have two functions, this one and this one, defined on the curve, right? Then of course what I'm going to do in an identity like this is evaluate them at the same point on the curve. So let's try it. Let's look at this point. What's gamma prime? I'm going to call it point, can I give it a name such as P, capital P? Why not, right? What is gamma prime at this point? Gamma is e to the little gamma. Its derivative is the same function. Little gamma equals 1 here, so it's e. Okay, now let's evaluate this. Where are we going to evaluate it? At the same point, of course. So gamma prime, well, let's look at this function. Gamma prime is log of capital gamma, right? The derivative of this function equals 1 over gamma. We need to evaluate 1 over that derivative. So 1 over this derivative equals 1 over, 1 over, and what does capital gamma equal here? E. Okay, so do you guys see the big difference between this formula, which is incorrect, that makes no sense, and it makes no sense because it was untethered from a geometric context. It was just an arithmetic game, and in the arithmetic game, you don't know what F represents, you don't know what G represents, you haven't specified what X represents. It's just an arithmetic exercise. And in the arithmetic exercise, the taxonomy, how these functions fit into each other, is what it's all about. And it's not automatically available. You cannot make any assumptions. You just have to specify things and be very careful. Here, this identity, because it is given in the geometric setting, implies that all of the functions, in order to be matched up, need to be evaluated at one and the same point on the curve. So the curve, the geometric object, gives you an absolute reference. Yeah, that should have been full stop. Gives you an absolute reference, right? And you can fall back on that absolute reference, and that's the absolute reference that tells you where functions are evaluated. And you just have to evaluate all of the available elements of the problem at one and the same point, and then you automatically have consistency. Does that make sense? So in a geometric setting, this formula is just so very simple and doesn't have any pitfalls, right? Whereas in the arithmetic setting, this formula is just one big pitfall. And here you have to enjoy the availability of an object that can be used as an absolute reference for things, right? It all goes back to the curve because the curve is what we're analyzing. Does that make sense? So things are simpler. But I actually think it's more complicated than that. I actually think it's a very ambiguous, vague statement. Change of variables, unless it's specified more clearly, is a very confusing task. And it's not clear what's being asked of you. And I just know that for a fact because when I teach tensor calculus, it's usually a problem that I give in the first week, which is to express the Laplacian and polar coordinates. And it's just a widowmaker of a problem. It's a humongous calculation, and it's a calculation where you can very easily do the wrong thing, and 3/4 of the students do the wrong thing. And if you gave it to seasoned researchers in applied math, 3/4 of them would do it incorrectly also, because I think it's fundamentally vague and ambiguous. Does that make sense? But when we do this in a geometric setting, where the Laplacian would be a characteristic of a field that has nothing to do with which coordinates you introduce, that will once again give you an absolute reference that defines an object, and then from that absolute reference that has no coordinates, you can then translate it into different coordinates, and it may or may not be an easy task, but it's a very clear task because you know what it needs to match up with. You know where the agreement needs to be. Just like here, you know that these derivatives are to be evaluated at consistent points.